Okay, let's start physics class 12 chapter 5, that is magnetism and matter. The first is introduction here. Magnetic phenomena are universal in nature. Okay, you can see magnetic phenomena everywhere in the universe, vast distant galaxies, the tiny invisible atoms, humans and beasts, all are permeated through and through with a host of magnetic fields from a variety of sources. The Earth's magnetism predates human evolution. The word magnet is derived from the name of an island in Greece called Magnesia, where magnetic ore deposits were found. That was as early as 600 BC. There was a island called Magnesia in Greece. Here there were magnetic ore deposits, so they called the ore found there as a magnet. In the previous chapter, we have learned that moving charges or electric currents produce magnetic fields. This discovery, which was made in the early part of the 19th century, is credited to Oersted, Ampere, Biot, and Sauer, among others. In the present chapter, we take a look at magnetism as subjects in its own right. Some of the commonly known ideas regarding magnetism are: the Earth behaves as a magnet with the magnetic field pointing approximately from geographic south to north. When a bar magnet is freely suspended, it points in the north-south direction. Okay, when there is a bar magnet freely suspended, it points to the north-south direction. The tip which points to the geographic north is called the north pole, and the tip which points to a geographic south is called as the south pole of the magnet. There is a repulsive force when north poles or south poles of two magnets are brought close together. Conversely, there is an attractive force between the north pole of a magnet and the south pole of the other. This is very obvious. Actually, this is very known fact. We cannot isolate the north or south pole of a magnet. If a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and south poles, known as magnetic monopoles, do not exist. It is possible to make the magnets out of iron and its alloys. We begin with a description of a bar magnet and its behavior in an external magnetic field. We describe Gauss's law of magnetism. We next describe how materials can be classified on the basis of their magnetic properties. We describe para, dia, and ferromagnetism. Okay, first we describe a bar magnet and its behavior in an external magnetic field, and we describe Gauss' law of magnetism. We next describe how materials can be classified on the basis of magnetic properties, that is para, dia, and ferromagnetism. And an important point here is north and south poles, known as magnetic monopoles, do not exist. Isolated magnetic north poles, known as magnetic monopoles, do not exist. Let's go to the bar magnet, the next main topic. They did not give, yes, they did not give topics wise. The bar magnet. We begin our study by examining iron fillings sprinkled on a sheet of glass placed over a short bar magnet. The arrangement of iron fillings is shown in figure 5.1. We take a short bar magnet, we take a sheet, we take the bar magnet and keep it on this paper or sheet, and when we pour iron fillings in that sheet or paper. This is the arrangement of iron fillings surrounding a bar magnet. The pattern mimics magnetic field lines. The pattern suggests that the bar magnet is a magnetic dipole. If we see, this is a bar magnet, and these are the field lines. Maximum at the poles and concentric circles like this, and going in to the south pole. This is the basic diagram. The pattern of iron filling suggests that the magnetic field, the magnet has two poles similar to the positive and negative charge of an electric dipole. As mentioned in the introductory section, one pole is designated the north pole and the other the south pole. When suspended freely, when suspended freely, these poles point approximately towards the geographic north and south poles respectively. The direction of the side of the bar magnet pointing towards the north side, the geographic north side, is called as the north pole, and the magnetic part or the magnetic side which is pointing towards the south pole is called south pole is called as the south pole of the magnet. A similar pattern of iron fillings is observed around a current carrying solenoid. When we take a current carrying solenoid, a similar kind of pattern is observed. Now let's continue. The magnetic field lines. The pattern of iron fillings permits us to plot the magnetic field lines. Okay, let's see, they gave a star mark here, a note point. In some textbooks, the magnetic field lines are called as magnetic lines of force. This nomenclature is avoided since it can be confusing. Unlike electrostatics, the field lines in the magnetism do not indicate the direction of the force on a moving charge. Okay, this is shown. The pattern of fillings permits us to plot the magnetic field lines. This shows both for the bar magnet and the current carrying solenoid in figure 5.2. For comparison, refer to chapter 1. Electric field lines of an electric dipole are also displayed in 5.2c. This is an electric dipole here where the field lines are coming radially out of the positive charge and going radially into the negative charge like this. The magnetic field lines are a visual and intuitive realization of the magnetic field. Their properties are, okay, let's read the statements paragraph again before we see the properties. Okay, they're saying the pattern of iron fillings permits us to plot the magnetic field lines. We saw the arrangement of fillings in the above figure is 5.1. This is the arrangement of fillings. I will erase this diagram. These are the fillings here. They're arranged in a specific way which we can draw the magnetic field lines from which we can draw the magnetic field lines. And this kind of arrangement of iron fillings is shown in both a bar magnet and also for a current carrying solenoid. And electric field lines of an electric dipole are displayed in the below figure. The magnetic field lines are visual and intuitive realization of the magnetic field. They are saying that the magnetic field lines are for our visual sake and for our understanding sake of the magnetic field. To understand and visualize the magnetic field, we use a concept called as magnetic field lines. Now, the properties of magnetic field lines are: the magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike the electric dipole where these field lines begin. Okay, tangent to the field line. Okay, that, yes, I was talking about, yes, when there are magnetic field lines, when we take tangent to that magnetic field line, it give the direction of the net magnetic field B at that point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. In figure 5.2a, B is larger around region 2 than in region 1. Let's see the diagram. Here, this is a bar magnet. Seems to be a bar magnet. This is very basic diagram here. The lines are going out from north pole to south pole outside the magnet, and from south pole to north pole inside the magnet. This gives us the total magnetic field lines representation where they are forming closed loops. The field lines of a bar magnet. And B diagram, a current carrying finite solenoid. This is a current carrying finite solenoid. If we observe both of these diagrams, we see both of them are quite similar. And C, this is an electric dipole at large distances. The field lines are very similar. The curves labeled 1, 2 are closed Gaussian surfaces. Okay, these are the different curves. One curve is seen here, and one more curve is here. This is also a curve, and there is a curve here. This is a curve as well, and similarly. These are all Gaussian surfaces, closed Gaussian surfaces. Now let's see this diagram as well. Calculation of the axial field of a finite solenoid in order to demonstrate its similarity to that of a bar magnet. B, a magnetic needle in a uniform. Actually, this is not needed, I guess, for now. It's in the next topic. The larger the number of the third property which you're seeing, the larger the number of field lines crossing per unit area, the stronger the magnitude of the magnetic field B. Here in this case, if we see this Gaussian surface and this Gaussian surface, there are more number of magnetic field lines passing through this Gaussian surface. So this is having a higher, this area is having a higher net magnitude of the magnetic field, whereas this Gaussian surface is having lesser magnitude of the magnetic field. Fourth property, the magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. Okay, the fourth and final and most actually interesting point is that the magnetic field lines never intersect. If they do, if you put a compass there, then the compass should show two different directions. That is not possible. So magnetic field lines do not intersect. When one can plot the magnetic field lines in a variety of ways. One way is to place a small magnetic compass needle at various positions and note its orientation. This gives us an idea of the magnetic field direction at various points in a space. We can plot the magnetic field lines in various kind of methods. One is we saw through the iron fillings method. Second method is taking a bar magnet and taking compass around it to observe the deflection in the compass to plot the magnetic field lines. Now let's go to the next main subtopic, that is bar magnet as an equivalent of a solenoid. In the previous chapter, we have explained how a current loop acts as a magnetic dipole. A current loop can act as a magnetic dipole. We mentioned Ampere's hypothesis that all magnetic phenomena can be explained in terms of circulating currents. Okay, we mentioned how Ampere's hypothesis was that all magnetic phenomena can be explained in terms of circulating current. The resemblance of the magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought as a large number of circulating currents in analogy with a solenoid. Basically, since we saw that a bar magnet and a solenoid are similar, we know that what a solenoid is. To define a magnet, a bar magnet, we can define it in terms of a solenoid. A solenoid is basically a large number of turns of coil which carries a finite amount of current, and we can define this in for a magnet, a bar magnet. That is, we can suggest that a bar magnet may be thought of as a large number of circulating currents, that is in analogy with a solenoid. Cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. The field lines remain continuous, emerging from one phase of the solenoid and entering into the another phase. One can test this analogy by drawing a small compass needle in the neighborhood of a bar magnet and a current carrying finite solenoid, and noting that the deflections of the needle are similar in both cases. Okay, the field lines remain continuous. They mentioned two information here. The first information, just like when you cut a bar magnet, you get two different small bar magnets. Same way, when we cut a solenoid, we get two different solenoids having weaker magnetic properties. The second information is that the field lines remain continuous, emerging from one phase of the solenoid and entering into the other phase. One of the face of the solenoid will have the north pole and other will have the south pole, basically saying one will have magnetic field lines coming out of it and other will have magnetic field lines going into it. How do we test that is, we can test this by moving a small compass needle, basically a compass, in a neighborhood in the vicinity or close to this bar magnet, and another current carrying finite solenoid with a measurable length, noting that the directions of the needle are similar in both cases. The deflections in the direction of the needle are same in both cases. To make this analogy more firm, we may calculate the axial field of a finite solenoid depicted in figure 5.3a. Okay, it's time to see the figure. Calculation of the axial field of a finite solenoid in order to demonstrate its similarity to that of a magnet. B, a magnetic needle in a uniform magnetic field B. The arrangement may be used to determine either B or the magnetic moment M of the needle. Okay, first thing we are calculating is the axial field, the field along the axis of a solenoid, to demonstrate its similarity to a bar magnet. And the second thing we are calculating is the arrangement, like we are calculating the magnetic moment of the needle. The magnetic needle in a uniform magnetic field B, the arrangement of this needle we can determine the magnetic moment m of the needle. Okay, this seems to be a solenoid. We take a small length element dx, and the total length, the half of the length is L, total length is 2L. This is the axis, this is point P, the radius is A, and the distance between the center to the point P is R. This is the magnetic field lines, the direction of magnetic field lines due to the compass, due to the solenoid, the needle will be directed in this direction, where angle with the horizontal is theta here. We can demonstrate that at large distances, this axial field resembles that of a bar magnet. We can demonstrate that when we take a large distance, this axial field created by a solenoid is similar to that of a bar magnet. The magnitude of the field at point P due to the solenoid is B equals mu naught by 4 pi 2m by r cube. Okay, this is the magnitude of the field at point P due to solenoid, which we have calculated or know from last chapter. This is also the far axial magnetic field of a bar magnet, which only may obtain experimentally. This is the solenoid one, but this is also the one for the far axial magnetic field of a bar magnet. Both solenoid and bar magnet have the same magnetic field, magnetic field value. Thus, a bar magnet and a solenoid produce similar magnetic field. Thus, magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. Okay, they're saying that the magnetic moment, because the magnetic field, axial magnetic field of a solenoid, the magnetic field produced axially by the solenoid, which is equals or similar to the same kind of bar magnet. So you can say the magnetic moment produced in the solenoid is equivalent to the magnetic moment produced in the bar magnet. Okay, let's go to the next main subtopic. The dipole in a uniform magnetic field. The dipole in a uniform magnetic field. Let's place a small compass needle of known magnetic moment m, allowing it to oscillate in the magnetic field. Actually, I'm having a little doubt about magnetic moment. What is magnetic moment? It's giving me two responses. I will choose this one. For different systems, current loop. For a current loop, the magnetic moment m is given by m equals Ia. So it seems that because we cannot find the magnetic moment for a bar magnet, because we can say the equivalent, we can calculate the magnetic moment for a solenoid, but we cannot calculate the magnetic moment for a bar magnet directly. So when we say that both are equivalent, we can easily calculate the magnetic moment of a similar solenoid and say the bar magnet also has a same magnetic moment. That is what we need to, that is why we need to study the similarity between both of them, I guess. Magnetic moment is a vector quantity that represents the strength and direction of a magnetic source. It essentially tells you how strong a magnet is and in which direction its magnetic influence acts. For a current loop, the magnetic moment M is given by IA, and for bar magnet, magnetic moment is the product of magnetic pole strength, and we can calculate the moment for a bar magnet, but I'm not sure why they did that. It points the south pole to the north pole of the magnet, where electric dipole moment, which is from negative to positive, here it is from south pole to north pole of a magnet. Electron or atom, okay, magnetic, how can it express or represent the strength and direction of a magnet? The direction of the magnetic moment vector, it tells you which way the magnetic field lines would emerge out of the magnet. The direction is found using the right hand rule. Curl your fingers in the direction of current, your thumb in the direction of the magnetic moment. Is it same thing like expressing for electric dipole moment? Expressing strength and direction of electric field. It seems to be similar. We know the relation that magnetic moment times magnetic field and dipole moment times electric field gives a torque. Fine, I guess. Okay, let that be. The dipole in a uniform magnetic field. Let's place a small compass needle of known magnetic moment M. How can we know the magnetic moment of a compass needle? No magnetic moment of a needle or any kind of substance. Actually, before that, how can we say the magnetic moment, interaction between magnetic moment? How does the magnetic moment define the interaction between magnetic field and this substance or this needle? Is it due to torque, where the cross product of the magnetic moment and magnetic field is taken? Is it similar in case of electric fields? The magnetic moment determines how strongly and in what way a magnetic object like a needle interacts with a magnetic field. And it's all about torque, and the interaction is very analogous to that of an electric dipole. Magnetic moment is equals to vector product or a cross product of m magnetic moment and the torque tries to rotate the needle, so the magnetic moment aligns with the magnetic field. No net force acts on the dipole in a uniform field. Only torque. A compass needle which has magnetic moment aligns itself with Earth's magnetic field due to its torque. If it is displaced slightly, it will oscillate due to the restoring torque. Potential energy, it is minus mb cos theta. Lowest energy with m is aligned with b, highest when anti-aligned 180 degree. Electric dipole moment is similar, I guess. The magnetic moment of a bar magnet is pole strength times the distance of the dipole length, similar to the electric dipole, where it was the dipole length times one of the charges. Okay, this magnetic dipole, or I mean this magnetic dipole moment, actually, is there any, I saw some relation between this magnetic moment and momentum before. I don't think it is related, but any relation between magnetic moment and momentum? Okay, there is a relation between magnetic moment and angular momentum. Magnetic moment and angular momentum. Imagine a charged particle like an electron moving in a circular orbit. Angular momentum L equals mvr. Okay. Magnetic moment, a moving charge, is a current loop. Okay, we will get I equals q by t, and t we can write it as 2 pi r, which is omega by, or theta by t, which is equals to, or 2 pi by t, which is equals to v or omega. So we can write t as 2 pi by omega. I guess that's what they might have written here. And instead of taking 2 pi only, they took 2 pi r. So the magnetic moment is equals to I into A, shall become qv by 2 pi r into pi r square. It will be qvr by 2. And this relation especially, okay. Okay, then that was interesting, but let's go. The dipole in a uniform magnetic field. Let's place a small compass needle of known magnetic momentum m, allowing it to oscillate in a magnetic field. Okay, this arrangement is shown in figure 5.3b. This is this side. Okay, these are actually two figures. This is the solenoid A, and this is 2. This is the compass needle placed in a magnetic field. We know the magnetic momentum of this compass, which is m. The torque on the needle is torque equals magnetic moment cross magnetic field in magnitude. It is tau equals mb sine theta. Here tau is restoring torque and theta is the angle between m and b. An expression for magnetic potential energy can be obtained on the lines similar to electrostatic potential energy. Okay, that is what we saw before. It was minus mb cos theta minus scalar product of mb. Here it says it's a restoring torque, meaning it will restore to a stable equilibrium position. Okay, restoring torque, and theta is the angle between m and b. An expression for magnetic potential energy can be obtained on the line similar to electrostatic potential energy. The magnetic potential energy um, the change in magnetic potential energy, can be given by the integration of tau theta or tau with respect to d theta, which will get it as mb sine theta. Mb will come outside. Integration of sine theta with respect to d theta, we will get it as minus mb cos theta, where we take one more angle as 90 degrees, it will become 0, where 90 degrees it is initial position. We have emphasized in chapter 2 that zero potential energy can be fixed at one's convenience. Taking the constant of integration to be 0 means fixing the zero of potential energy at theta equals 90 degree. That is, when the needle is perpendicular to the field, we took theta equals 90 degree, where the potential energy to be 0. Shows that equation 5.3 shows that energy is potential energy is minimum minus mb at theta equals 0 degree, most stable position, and maximum at 180 degree, most unstable position. Okay, then it is potential energy is not negative or maximum at 90 degrees, where it is the 0, potential energy is 0. Okay, there is an example question here. What happens if a bar magnet is cut into two pieces, that is transverse to its length and along its length? They're saying two ways to cut a bar magnet. If this was a bar magnet, north and south, what if we cut it like this? And one more way is, what if we cut it like this? What will happen? A magnetized needle is the next question is, a magnetized needle is in a uniform magnetic field, experiences a torque but no net force. Okay, a magnetized needle in a uniform magnetic field experience a torque but no net force. An iron nail near a bar magnet, however, experiences a force of attraction in addition to torque. Why? Here the iron nail, wait, not iron nail, because the magnetized needle is acting as a dipole, so that is the reason it is experiencing a torque and no net force. Let's see this fourth question. Must every magnetic configuration have a north and south pole? What about the field due to a toroid? We did not have that in the previous chapter, but fine. Two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. Okay, there are two looking iron bars A and B, one of which is known to be magnetized. A and B, two iron bars, one of it is for sure magnetized. We don't know which one. How would one ascertain whether or not both are magnetized? If only one is magnetized, how does one ascertain which one? Using nothing else but the bars A and B. Okay, let's see the solution to the first question. When we cut a bar magnet transverse and along its length, in both of the cases, in either case, one gets two magnets, each with a north and a south pole. Second question, a magnetized needle, if it is in a uniform magnetic field, experiences a torque but no net force. An iron nail near a bar magnet, however, experiences force of attraction in addition to torque. Y. No force if the field is uniform. The iron nail experiences a non-uniform field to the bar magnet. There is induced magnetic moment in the nail. Therefore, it experiences both force and torque. The net force is attractive because the induced south pole, say in the nail, is closer to the north pole of the magnet than induced north pole. Okay, they're saying that the first point they're saying, if the like in case of If in case of the needle, it is placed in a uniform field, so it experiences only a torque, and if it is in a uniform field, there will be no force. But the iron nail experiences a non-uniform field, meaning it's a non-uniform magnetic field, that is due to the bar magnet. And due to this non-uniform magnetic field, there is an induced magnetic moment in the nail. The nail will get magnetic moment which is induced due to the bar magnet, due to which it experiences both force and torque. This force is attractive in nature because this induced south pole, let's assume if the closest end is south pole, and north pole of the magnet which is inducing a south pole which is closer to the north pole of the magnet than induced north pole. Okay, see, must every magnetic configuration have a north pole and a south pole? Must every magnetic configuration have a north pole and a south pole? What about the field due to a toroid? It is not necessary that every configuration must have a north and south pole. True only if the source of the field has a net zero magnetic moment. This is not so for a toroid or even for a straight infinite conductor. Okay, this is not necessarily true only if the source true only if the source of the field has a net zero magnetic moment. This is not so for a toroid or even for a straight infinite conductor. Okay, then fourth question is two identical looking bars A and B, which one are given, one of which is definitely known to be magnetized. We do not know which one. How would one ascertain whether or not both are magnetized? If one is magnetized, how do we ascertain which one? Using nothing but bars A and B. Try bring different ends of the bar closer. A repulsive force in some situation establish that both are magnetized. If it is always attractive, then one of them is not magnetized. In a bar magnet, the intensity of the magnetic field is strongest at the two ends poles and weakest at the central region. This fact may be used to determine whether A or B is a magnet. In this case, to see which one of the two bar is a magnet, pick one, say A, and lower one of its end first on one of the ends of the other, and then on the middle of B. If you notice that in the middle of B, A experiences no force, then B is magnetized. If you do not notice any change from end to middle of B, then A is magnetized. Okay, this is basic magnetic playing with the magnets kind of thing. Okay, let's go to the next topic, the electrostatic analog. Comparison of equations 5.1, 5.2, and 5.3. 5.1, the magnetic field at the axis of a solenoid or a bar magnet, mu naught for very large distances, that is mu naught by 4 pi times 2m by r cube. And equation 5.2, tau equals m cross b. And 5.3, which is the change in potential energy, which is taking the perpendicular portion to have zero change in potential energy. It is minus m dot b, or minus mb cos theta. These are the three equations. Comparison of these three equations with the corresponding equations for electric dipole suggests that magnetic field at a large distances due to bar magnet of magnetic moment m can be obtained from the equation for electric field due to an electric dipole of dipole moment p by making the following replacements. when we take the magnetic field at large distance due to a bar magnet having magnetic moment m, when we compare these equations due to an electric dipole having a small electric dipole from large distances, the same electric field produced based on calculation of the electric field, same way in same equation, just substituting with E with B, dipole electric dipole moment with magnetic dipole moment, and 1 by 4 pi epsilon naught with mu naught by 4 pi, we will get the same answer, or we will get the correct answer. In particular, we can write down the equatorial field B for bar magnet at a distance r, for r to be very very greater than L, where L is the size of the magnet, where B, which is equals to mu naught m by 4 pi r cube. This is the equatorial field of a bar magnet. Likewise, the axial field of a bar magnet, where r is greater than L, is BA, which is equals to mu naught by 4 pi 2m r cube, 2m by r cube. Equation 5.5 and 5.1 in vector form. Table 5.1 summarizes the analogy between electric and magnetic dipole. Dipole moment, it is P, here it is M, here it is 1 by 4 pi, 1 by epsilon naught, here 1 by, mu naught. Equatorial field for a short dipole minus P by 4 pi epsilon naught r cube, it is minus mu naught M by 4 pi r cube. Axial field for a short dipole, 2p by 4 pi epsilon naught r cube, mu naught to m by 4 pi r cube. External field torque, which is electric dipole moment times electric field, magnetic dipole moment cross magnetic field, external field energy minus p dot E minus m dot B. Very very similar. Let's see the example given here. This is a figure. What this figure shows is figure 5.4 shows a small magnetized needle P placed at point O. There is a small needle here. It is placed at point O, which is center. The arrow shows the directions of its magnetic moment. The other arrow shows different positions and orientations of the magnetic moment of other identical magnetized needle Q. Okay, they are saying that here there is a small magnetized needle P that is placed at point O, and the arrow shows the direction of its magnetic moment. The magnetic moment is from south pole to north pole, so this is the direction of the magnetic moment of that first needle. There are two needles, not noodles but needles. There are two needles here, and one needle we keep at the middle. It is showing upwards like this, and other needle we move around to see its deflection. Now the arrow shows the direction of its magnetic moment. The other arrow shows different positions and orientations of magnetic moment of another identical magnetic needle Q, in which configuration the system is not in equilibrium. In which configuration is the system stable and unstable equilibrium. Which configuration corresponds to the lowest potential energy among all the configurations shown. The first position is, let's remove this. Okay. The first position of the second needle placed is here. The second position is here. third position this way, fourth this way, fifth this way, and sixth here. Okay, the first they asked in which configuration the system is not in equilibrium. Potential energy of the configuration arises due to potential energy of one dipole. That is, let's assume here, since we are moving Q, say Q here, in the magnetic field due to other, that is P, use the result that field due to P is given by equations 5.4 into 5.5. Basically, this is axial. Wait. This is equatorial and this is axial. And where axial, it is double the equatorial for finding the magnetic field due to the needle placed at the center, where MP is the magnetic moment of the dipole P. Equilibrium is stable when MQ, the magnetic moment of Q, is parallel to the magnetic moment of, the dipole B, and unstable when it is anti-parallel to P. Basically, the magnetic field due to the needle P, which is PP, and the magnetic moment of needle Q, which is MQ, torque, which is equals to MQ cross BP, where it is torque is torque is it's an equilibrium when MQ is parallel to BP. When angle between them is 0, when angle between MQ and BP, which is equal to 0, then sine 0 equals 0, so torque also equals 0. It's in a stable equilibrium. When there is a slight deflection, meaning it will restore, there will be a restoring torque that is observed. In case where theta equals 0 degree, where both of them are parallel, in this case here, or in this case as well, angle between them, yes, in these two cases I believe it is stable equilibrium, and these two cases unstable equilibrium. And in these two cases here, I believe in these two here, these two, I believe there will be no equilibrium. Equilibrium is stable when MQ is parallel to BP and unstable when it is anti-parallel to BP. For instance, for configuration Q3, for which Q is along perpendicular bisector of P, the magnetic moment of Q is parallel to the magnetic field at position 3. Hence, Q3 is stable. Q3, which is stable. Wait. Fine, that one I'll see later, I guess. They said PQ3 and PQ6. Q3 and Q6 were opposite directions. They are stable, whereas Q5 and Q4, which is these two, are in unstable equilibrium, and PQ6 They did not mention anything, which is C. PQ1 and PQ2 are not in equilibrium. That is indeed what I said. But this one I will see again. PQ6 has the lowest potential energy among all the following. Okay, then before going to the next main topic, that is magnetism and Gauss law, they gave a passage about Gauss here. Let's just read it out loud. Carl Friedrich Gauss, 1777 to 1855. He was a child prodigy and was gifted in mathematics, physics, engineering, astronomy, and even land surveying. The properties of numbers fascinated him, and in his work, he anticipated major mathematical development and later times, along with Wilhelm Welser. He built the first electric telegraph in 1833. His mathematical theory of curved surface laid the foundation of the later work of Riemann. The magnetism and Gauss law. In chapter 1, we studied Gauss law for electrostatics. Okay, in figure 5.2c, we see that for a closed surface represented by I, this is the electric dipole figure. The number of lines leaving the surface is equal to the number of lines entering it. Entering it. This consistent with the fact that there is no net charge enclosed by the surface. However, in the same figure for the closed surface 2, there is a net outward flux. So it does not include a net positive charge. The situation is radically different for magnetic fields where continuous and okay, here this situation is radically different for magnetic fields which are continuous and form closed loops. Examine the Gaussian surfaces represented in 1 or 2 in figure 5.2a or 5.2b. Okay, let's see the first figure here. Here, this is the first diagram here. Here there is a net magnetic field. I mean, there will be a flux. No, there will be no flux in this case because there is no net charge enclosed, because two magnetic field lines are entering and two are leaving. There is no net magnetic flux in this case. And in this case, though, all are leaving. There is a net outward flux. All are leaving like this. Here as well, they are all leaving. So there must be a magnetic field enclosed. I mean, not magnetic field, a charged enclosed. A charge is enclosed. That is the reason, according to Gauss rule, there must be a flux. I mean, there must be, yes, there is a flux. Okay, they're saying, let's observe the magnets here as well, the Gaussian surface for the magnet here as well. Now, for a magnet, if we see, let's observe this Gaussian surface. Two are entering and two are leaving. And in this case as well, these are all entering, these are all leaving. So the net flux should be 0. And in this case as well, 2 are entering, 2 are leaving. Net flux is 0. Here a similar situation. All these lines are entering, all these lines are leaving. Now let's see the explanation. But that was interesting to see. Let's read the passage from the start again. In chapter 1, we studied Gauss' law for electrostatics. We studied that for a closed surface represented the number of field lines leaving the surface is equal to the number of field lines entering it. This is consistent with the fact that no net charge is enclosed by the surface. However, in the same figure for closed surface 2, there is a net outward flux since it does include a net positive charge. The situation is radically different for magnetic fields which are continuous and form closed loops. Examine the Gaussian surfaces represented by 1 and 2 in figure 5.2a or 5.2b. Both cases visually demonstrate that the number of magnetic fields leaving the surface is balanced by the number of field lines entering it. The net magnetic flux is 0 for both the surfaces. This is true for any kind of closed surface. Now there seems to be a figure here. Okay. Consider a small vector area element delta S of a closed surface S as in figure 5.5. Okay, delta S, maybe this surface here, is a what? Is a closed surface. It's a surface element, it's a closed surface S. The magnetic flux through AS, what does A double dot S is defined as delta phi B. Okay, the magnetic flux is defined as delta phi B, and which is equals to B times magnetic field times area. Okay, this is this is basically similar to the electric flux, where electric flux was equal to electric field times the surface area element, or EA cos theta. Similar to that, it is B delta S, the magnetic field, times the surface element, which is the magnetic flux. This is an area element, this is the magnetic field lines, where B is the field at delta S. We divide S into many small area elements and calculate the individual flux through each. Then the net flux B, where net flux B equals all the individual elements, which is summation of B delta S, should be equal to 0. That is what we saw, because the number of field lines entering will be the same as the number of field lines leaving. So the net flux should be 0, where all stands for all the area elements of delta S. Compare this with the Gauss law for electrostatics. The flux through a closed surface in that case is given by E summation E delta S, which is given by Q by epsilon naught, where Q is the electric charge enclosed in the surface. The difference between the Gauss law of magnetism and that of electrostatics is a reflection of the fact that the isolated magnetic poles, also called monopoles, are not known to exist. Maybe if there were monopoles, which would give rise to all the magnetic fields, and would, and the other south pole to be the end of all magnetic fields, then maybe it would have been exactly same as electrostatics case. But that is not the case, because there is no monopoles existence. There are no sources like the positive charge, or sinks like the negative charge of the magnetic field. The simplest magnetic element is a dipole, or a current loop. All magnetic phenomena can be explained in terms of an arrangement of dipoles or current loops. Thus, Gauss' law for magnetism is the net magnetic flux through any closed surface is zero. That's great to hear, or that is simple to hear, I guess. Many of the diagrams given in figure 5.6 show magnetic field lines. Thick lines in the figure wrongly, okay, point out what is wrong with them. Some of them may describe electrostatic field lines correctly. Point out which ones. Okay. It seems that there are diagrams given and they are showing magnetic field lines to be wrong representation. Point out what is wrong with them, and some of them describe electrostatic field lines correctly. Blue lines are electric field lines. Blue electric field lines, and dark or black, which is magnetic field lines. So in this case, there are no magnetic field lines, only electric field lines. It is indeed correct, but I do not think this is possible. There is no flux in this direction, or it might be actually. Okay, these are the magnetic field lines and electric field lines. These are the magnetic field lines. Magnetic field lines seem to be correct, but I do not think the electric field lines are possible here where they form concentric loops. This is not correct. And in this case, this is an empty space here. And we know that neither electric field lines nor magnetic field lines intersect. So not possible. And it is possible for magnetic field lines to form concentric loops. And let's see figure C. Magnetic field lines are completely circular like this, concentric loops. This is, I guess, possible. And the electric field lines seem to be like this, which I do not understand clearly. They are not mention any arrow mark here. Okay, let's go to the diagram B. It is indeed possible for magnetic field lines to be like this. As for electric field lines, I'm not too sure. Let's go to figure F here, where this seems to be a negative charge and this seems to be a positive charge. Okay, possible indeed. And I'm not sure what that figure means. There seems to be a small. Okay, this whole thing is a magnet. This whole thing is a magnet. And the magnetic field lines are going here like this. Might be possible. Let's see the answer. A, this diagram. Let's see what's wrong with this diagram. Let's see how many actually are wrong and how many actually are right. First diagram and A and B are wrong. A wrong, B wrong, C right, D wrong, E right, and F wrong, G wrong, and G also wrong. Okay, let's see what's wrong with them. A is wrong. Magnetic field lines can never emanate from a point. Seems I have been confused with magnetic and electric field lines. Okay, these are emanating from a single point. Over any closed surface, the net flux of B must always be zero. That is, pictorially, as many field lines should seem to enter the surface as the number of field lines leaving it. The field lines shown in fact represent electric field of a long positively charged wire. The correct magnetic field lines are circling the straight conductor I described in chapter 4. Okay, it seems blue lines are electric or magnetic field lines. I mean not electric, I mean blue lines are magnetic field lines, and dark color lines are, let's leave that reaction. I'm not sure myself. Wrong, magnetic field lines like electric field lines can never cross each other. That's what I said, can never intersect each other, because otherwise the field at a point of intersection is ambiguous, meaning two directions it will show. There is further error in the figure. Magnetostatic field lines can never form closed loops around empty space. A closed loop of static magnetic field line must enclose a region across which a current is passing. By contrast, electrostatic field lines can never form closed loops, neither in empty space nor when the loop encloses charges. Okay, the first thing wrong is no intersection. The second thing wrong is there must be some current carrying element here, so it is not possible for them to be without this current. There is no possibility for forming loops here, and electrostatic field lines can never form loops. And third one, C is right, which is this diagram is right, this diagram, it is right. How so? Magnetic lines are completely confined within a toroid. Nothing wrong here in field lines forming closed loops, since each loop encloses a region across with a current passes. Note, for clarity of figure, only a few field lines within the toroid have been shown. Actually, the entire region enclosed by the windings contains the magnetic field. Okay, D is wrong. How so? D is this figure. Field lines due to solenoid at its end and outside cannot be so completely straight and confined. Such a thing violates Ampere's law. The line should curve at both ends and meet eventually to form closed loops. They are saying should not be like this, but like this to form loops like this. Figure E is right, so this is right. These are field lines outside and inside of a bar magnet. Note carefully that the direction of field lines inside, not all field lines emanate out of North Pole or converge into South Pole. Around both the North Pole and the South Pole, the net flux of the field is zero. Okay, the figure F is wrong. How so? That is, the field lines cannot represent, okay, they are magnetic field lines, so of course they will be wrong. These field lines cannot possibly represent a magnetic field. Look at upper region. All the field lines seem to emanate out of the shaved plate. The net flux through a surface surrounding the shaded plate is not zero. It is impossible for a magnetic field. The given field lines in fact show the electrostatic field lines around a positively charged upper plate and a negatively charged lower plate. The difference between figure 5.6e and F should be carefully grasped. Okay, the eighth, I mean the G figure, which is this one, is also wrong. Wrong. Magnetic field lines between two poles pieces cannot be precisely straight at the ends. Some fringing of lines is inevitable, otherwise Ampere's law is violated. This is also true for electric field lines. There must be some distortion. That's what they're saying here. Okay, one more example here. Let's read the example. Question: a magnetic field line shows the direction at every point along which a small magnetized needle aligns. At that point, to the magnetic field lines also represents the lines of force on a moving charge particle at every point. This is not true because we saw note point. That is not the case. The electric field does show the direction of force, but a magnetic field lines do not show the force. That is the reason the NCERT textbook actually used magnetic field lines instead of magnetic lines of force, because that is wrong and it does not show the represent the lines of force on a moving charged particle. But something they mention in the question is that magnetic field lines show direction at every point along which a small magnetized needle having a magnetic moment m aligns at that point. It will give the direction of the alignment of the needle. Maybe it's the tangent of the magnetic field. If magnetic field, okay, let's skim through the next question. If magnetic monopoles existed, how would the Gauss law of magnetism be modified? Maybe if magnetic monopoles did exist, it would be the strength of the magnetic monopole by mu naught or times mu naught. Maybe that would be the case. Does a bar magnet exert a torque on itself due to its own field? Okay, they are saying, does a bar magnet exert a torque on itself due to its own field? Does one element of a current carrying wire exert a force on another element of the same wire? They asked two questions here. If there is a bar magnet, does it experience torque? Does it spin around due to its own magnetic field? And does a current carrying wire exert a force on another element of the same wire? I do not think that is the case. Let's see more explanation in the answer. Okay, let's read the fourth question before that. Magnetic field arises due to charges in motion. Can a system have the magnetic moments even though its net charge is zero? Okay, they gave a statement that magnetic field arises that is due to charges in motion. That is the reason magnetic field arises. Can a system have magnetic moments even though its net charge is zero? Okay, fine. Let's see the solution. The first question is, magnetic field lines show the direction at every point along which a small magnetized needle aligns at that point. So the magnetic field lines also represent the lines of force on a moving charge particle at every time. The force is always perpendicular to the magnetic field as well as the velocity vector, so it does not show. The magnetic force is always normal perpendicular to magnetic field. Remember, magnetic force QVB, I mean QB cross B, it is misleading to call magnetic field lines as lines of force. Now, second question, if magnetic monopoles existed, how would the law of magnetic how would the Gauss law of magnetism be modified? Gauss law of magnetism states that flux of B through any closed surface is always zero. If magnetic monopoles existed, the right hand side would be equal to the monopole enclosed by S, analogous to Gauss law of electrostatics. So it will be mu naught, it will be equal to mu naught times Qm, where Qm is the monopole magnetic charge enclosed by the surface. C. Does a bar magnet exert a torque on itself due to its own field? Does one element of a current carrying wire exert a force on another element of the same wire? Does that happen? No, there is no force or torque on an element due to the field produced by the element itself, but there is a force or torque on an element of the same wire. For the special case of a straight wire, this force is zero. Okay, they are saying if it is the same element, the like in case of a bar magnet, the magnetic field produced by it will not cause a torque on itself, but in case of different elements it is possible, but it is not possible in case of a straight line. In case of a straight line the force is zero, but in case of other cases, maybe in case of a solenoid, if we take, I'm not too sure, but in such cases it might be possible. The fourth question is, magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is zero? Magnetic moment is I times A, so even though net charge enclosed might be zero, it is possible. The average of a charge in a system may be zero, yet the mean of the magnetic moments due to various current loops may not be zero. We will come across such example in connection with paramagnetic material where atoms have net dipole moment through their net charge is zero. Okay, they're saying even though the net charge may be zero, net charge, or yes, net charge is zero, the average of the magnetic moments due to various current loops may not be zero. We will see more about this in paramagnetic material where atoms having a net dipole moment though their net charge is zero. Let's go to the next main topic. Magnetization and magnetic intensity. Actually, I think it's better to take a 5 to 10 minute break. See you after the break. Okay, then, okay, I have to a little more than, okay, a little more than 5 to 10 minute break, but fine, let's continue with magnetization and magnetic intensity. The Earth abounds with a bewildering variety of elements and compounds. In addition, we have been synthesizing new alloys, compounds, compounds, and even elements. One would like to classify the magnetic properties of these substances. In the present section, we define and explain certain terms which will help us carry out this exercise. Basically, the earth has many kind of variety of elements and compounds, and after that, after these compounds that earth naturally has, we are also synthesizing new alloys and compounds and even elements. But like, we would like it to classify these magnetic properties of these new elements, compounds, and natural elements as well. We define and explain certain terms which will help us carry out such a classification or identifying the magnetic properties. I have seen that a circulating electron in an atom has a magnetic moment. When a circulating electron in an atom, it has a magnetic moment. In a bulk material, these moments add up vectorially and they can give a net magnetic moment which is non-zero. In a single atom, when an electron revolves around the nucleus, it will have a magnetic moment. And in case of a bulk, where we have a bulk of that material having numerous number of these atoms, these moments, these individual moments, add up vectorially and they give a net magnetic moment which is not zero. We define magnetization M of a sample to be equal to its net magnetic moment per unit volume. Basically, because individual atoms have individual magnetic moments, we define, and there is a net magnetic moment for a whole substance, we define magnetization M of a sample magnetization is equal to the net magnetic moment per unit volume. Basically, for if we take one block of that substance, which is, let's assume, 1 meter cube, then we define magnetization if the net magnetic moment of that 1 meter cube of substance is some 10 units, then the magnetization is also 10. If it was 100 units of net magnetic moment, and it was, the total substance was around also 10 meter cube, then the magnetization of that substance would be 1 unit magnetization. Basically, magnetization of a sample, it's equals to the net magnetic moment per unit volume. Magnetization, which is equals to magnetic moment, net magnetic moment of the entire block or substance by unit volume, or volume by the total volume of the block. Magnetization is a vector with dimensions L power -1 ampere and is measured in a unit of ampere per meter. Consider a long solenoid of n turns per unit length and carrying a current I. The magnetic field in the interior of the solenoid was shown to be given by B naught equals mu naught Ni. If the interior of the solenoid is filled with a material with non-zero magnetization, the field inside the solenoid would be greater than B naught. The net B field in the interior of the solenoid may be expressed as B equals B naught plus Bm. Okay, they're saying if we consider a long solenoid having n number of turns per unit length, there are n number of turns per unit length of this solenoid, and is carrying a total current of I, the magnetic field in the interior of the solenoid, we know the formula is B naught, which is equal to mu naught Ni. And if this interior of this solenoid is filled with a material with non-zero magnetization, basically if it was not air or vacuum in the gap of the solenoid and some other substance, and this substance is having a net magnetic moment per unit volume of the substance, meaning it's having a magnetization, a non-zero magnetization, the field inside the solenoid will be greater than B naught. B naught is mu naught times Ni. When we add a substance having a non-zero magnetization value, then the field inside the solenoid, it will be amplified. It will be greater than the initial B naught value. And the net B field, the net magnetic field in the interior of the solenoid can be expressed as B naught plus Bm. B naught is the initial magnetic field value and Bm is the field contributed by the material core. It turns out that the additional field Bm is proportional to the magnetization of the material, and it is expressed as, which is Bm, which is equals to mu naught times magnetization, where mu naught is the same constant permeability of vacuum that appears in the Biot-Savart law. There seems to be an error here, that is permeability, not permittivity. Okay, magnetization is the unit volume, the magnetic moment per unit volume of a conductor is called as the magnetization. And when we have a soft iron core, we might have wondered, in case of the motor we have a coil as well as a soft iron core in that coil, why that is placed. And in case of the previous chapter in a moving coil galvanometer, we saw there was a soft iron core inside the coil, and we can understand here that those are soft iron core, it is having a magnetization of greater than zero, so it will amplify the magnetic field inside this solenoid. So the net magnetic field will be B naught plus Bm, where Bm is the mu naught times magnetization of the conductor or the material. And here mu naught is the same constant, appears in Biot-Savart law. It is convenient to introduce another vector field H called the magnetic intensity, which is defined by H, which is equal to B by mu naught minus M, where H has the same dimensions as magnetization measured in terms of ampere per meter. Thus, the total magnetic field B is written as mu naught H plus M. Okay, where B equals mu naught times H plus M, where B, which is equals to mu naught times H plus mu naught times M, where mu naught times M, which is equals to mu naught times H plus mu naught times M, which is basically the Bm value. Mu naught times H, where why do we introduce such a constant? Where I believe mu naught times H, which is same as B naught value, so that means B naught, which is equals to H, then mu naught Ni is equals to H, which is not equal to H but mu naught H, or H times mu naught. So mu naught times Ni, and this is not mu naught times Ni. This is H. So are they defining n times I, the number of loops, or is this L times? No, it is I. N times I, the number of terms, times the current, which is the H, where H has the same dimensions as M here and is measured in terms of ampere per meter, which if it was H, which is equal to N times I, ampere times this is number of terms per unit length, so ampere per meter indeed. We repeat our defining procedure. We have partitioned the contribution to the total magnetic field inside the sample into two parts. One, it is due to external factors such as the current in the solenoid. This is represented by H. Okay, the magnetic field due to the other factor, that is other factor, is represented by H. The other is due to the specific nature of the magnetic material, namely M. There are two factors that decide the magnetic field inside maybe a solenoid if we take, and that is represented by the external factors, the total current in the solenoid, or we can take the magnetic material, that is magnetization of the material. The lateral quantity can be influenced by external quantities, latter meaning the magnetization. External factor, this influence is mathematically expressed by magnetization, which is chi h, where chi, a dimensionless quantity, is appropriately called magnetic susceptibility. It is a measure of how magnetic material responds to an external field. Chi is a small and positive value for materials which are called paramagnetic. It is small and negative for materials which are termed as diamagnetic. In the latter case, where M, magnetization, and H are opposite in direction from 5.12 and 5.13, we obtain that magnetic field which is equals to mu naught 1 plus mu naught chi h, which is chi h, which is equal to if it is outside, then mu naught h into 1 plus r, we'll get mu naught times mu naught r h, and mu for medium, permeability of medium, times h, where mu naught r, which is equals to 1 plus chi, is a dimensionless quantity called relative magnetic permeability of the substance. Its analog of dielectric constant in electrostatics. The magnetic permeability of substance is mu, and it has the same dimensionless unit as mu naught. Okay, to understand this, let's read this again. They introduced another factor here, that is H, that is the external factors. Okay, that H is basically N times I, and here this paragraph we have partitioned the contribution of the total magnetic field inside the sample into two parts. One is due to external factors such as the current in the solenoid, that is by H, this is represented by H. The other is due to specific nature of the magnetic material. namely magnetization. The latter quantity, meaning magnetization, can be influenced by external factor. This influence is mathematically expressed as magnetization, which is equal to chi h. Does that mean this seems to be written wrong? M, which is equals to chi h, where chi is susceptibility. Okay, I think it will know it. Does that mean as the h factor that is current or number of turns of a solenoid or any kind increases, the magnetization property also increases, and the rate or and the amount or sensitivity of increase with respect to the h is the magnetization. I do not know what I wrote, but is correct or not, but fine. Number of n increases the external field h, where since m is equals to chi h, a stronger h induces more magnetization in the material, where how much m material gains per unit h. It's not the magnetization itself, but the sensitivity or responsiveness of the material to the applied field. If chi equals 0, the material doesn't magnetize at all. Like air, if chi is large and positive, material becomes strongly magnetized like soft iron. If chi is negative, material opposes the applied field like diamagnetic material. How can increasing h possibly increase magnetization of a material? Magnetization, inside there are atoms, tiny magnetic dipoles. Due to electrons spinning and orbiting in unmagnetized material, these dipoles are randomly oriented, so net magnetization is 0. When you apply magnetic field H, it tries to align these dipoles in direction of the field. So magnetization M is net alignment of the internal magnetic dipoles caused by the external fields. Applying stronger external field, stronger torque on atomic dipoles, this causes more dipoles to align in the direction of the field. As more dipoles align, the magnetic moment per unit volume M also increases. So more H at some point magnetically saturated. They said there is an amplification in the magnetic field inside that if we place a ion core. Is the magnet is the net magnetic field amplification inside, for example, a solenoid when uh, a substance with a non-zero magnetization is placed due to the alignment of individual, or due to the addition of the aligned individual magnetic dipoles which produce individual magnetic fields. And this magnetization is equals to mu naught times magnetization. And magnetization definition, magnetization, we have seen the circulating electron in an atom has magnetic moment in a bulk material. These moments add up vectorially and they can give a net magnetic moment which is non-zero. We define magnetization M of a sample to be equal to its net magnetic moment per unit volume. Net magnetic moment per unit volume. Okay, but here they are saying it is only possible when there is already a magnetic field. Okay, let's continue reading. I will read the whole thing once again. I think it's better that way. Magnetization and magnetic intensity, the bonds with a bewildering variety of elements and compounds. In addition, we have been synthesizing new alloys, compounds, and even elements. One would like to classify the magnetic properties of these substances. In the present section, we define and explain certain terms which will help us to carry out this exercise. We have seen that a circulating electron in an atom has a magnetic moment in a bulk material. These moments add up vectorially and they can give a net magnetic moment which is non-zero. We define magnetization M per sample to be equal to its net magnetic moment per unit volume. Capital M magnetization is a vector with dimensions ampere per L and is measured as ampere per meter. Consider a long solenoid of n turns per unit length and carrying current I. The magnetic field in the interior of the solenoid was shown to be given by B naught, which is equals to mu naught Ni. If the interior of the solenoid is filled with a material with non-zero magnetization, the field inside the solenoid will be greater than B naught. The net B field in the interior of the solenoid may be expressed as B equals B naught plus Bm, where Bm is the field contributed by the material core. It turns out that this additional field Bm is proportional to the magnetization M of the material and is expressed as Bm, which is equals to mu naught M, where mu naught is the same constant permeability of vacuum that appears in the Biot-Savart's law. It is convenient to introduce another vector field, let's say H, called magnetic intensity. H is magnetic intensity, magnetic intensity, which is magnetic intensity, which is equal to N times I. Okay, where H has the same dimensions as M and is measured in units of ampere per meter. Thus, the total magnetic field is written as B equals mu naught magnetic intensity plus magnetization. We repeat our defining procedures. We have partitioned the contribution to total magnetic field inside the sample into two parts, one due to external factors such as current in a solenoid. This is represented by magnetic intensity H. The other is due to specific nature of okay, I was at we repeat our defining procedure. We have partitioned the contribution to the total magnetic field inside the sample into two parts, one due to external factors such as the current in the solenoid, and this is represented by H. The other is due to the specific nature of the magnetic material, namely M. The latter quantity can be influenced by external factors. This influence is mathematically expressed as M equals chi H, or magnetization, which is equals to chi times magnetic intensity, where chi, a dimensionless quantity, is appropriately called magnetic susceptibility. It is a measure of how a magnetic material responds to an external field. Basically they are saying the degree of the alignment of the magnetic dipoles, or yes, magnetic dipoles, the degree of the alignment of the magnetic dipoles for unit magnetic field is, we can say, it is a magnetic susceptibility of that material. It is a measure of how a magnetic material responds to an external magnetic field. Chi is small and positive for materials which are called paramagnetic. It is small and positive for materials which are called as paramagnetic. It is small and negative for materials which are termed as diamagnetic. Okay, in latter case, which is it is small and negative, M and H are in opposite direction. Magnetization and magnetic intensity are in opposite direction. So in the former case, that is when chi is positive for materials, it word is better, I think. Okay, the chapter was magnetism and matter, I believe. Yes, magnetism and matter. They're saying that Kyle, let's take first case. Case 1, chi, that is magnetic susceptibility, positive and small paramagnetic substances. When there is a conductor like this and there is a field, let's assume this is the direction of the field. This is the direction of the field. It's going into the conductor as well. And in case of paramagnetic substances, the magnetic intensity should also be in this direction. Intensity should also be in this direction. So magnetization will also be in this direction. When magnetization is in this direction, the magnetic dipoles will be arranged so that the magnetic field, the net magnetic field, will be coming like this and going through like this. In such a case, this will become the south pole and this will become the north pole. If this was a bar magnet, that is in giving this magnetic field, when south pole and north pole are created like this, these both will be attracted here, attraction here. Maybe that is the reason paramagnetic substances are attractive in nature. That is when chi is positive and small. In the second case, case 2, chi, that is negative and smaller. It seems I have forgotten to extend the pages. Okay, there. Okay, then yes, case 2, where chi, which is negative and small, here it is a diamagnetic substance, where the same kind of substance, if we take, it's not the same material, it's just similar kind of block of substance, where this is the magnetic field magnetic field here, then the magnetization, I believe, would be acting in this direction, and H will be acting in this direction. So the magnetic field lines will be coming out like this and going in like this. So in such a case, if this was a bar magnet producing this field, if this was north and south pole, since magnetic field lines are coming out like this will become a north pole, this will become a south pole, and there will be repulsion here. And okay, chi is small and positive for materials which are called paramagnetic. It is small and negative for materials which are termed as diamagnetic. In negative cases where M and H are opposite in direction, and from this equation and this equation, I mean this equation and this equation, we will get that B will be, which is equal to mu naught H plus M, which is equals to chi M. I mean not chi M, it is chi H, and chi we can take common, mu naught, not chi but magnetic intensity we can take common, it will become 1 plus chi. That is what we got here. And from that 1 plus chi can also be written as 1 plus chi, which is equals to relative permeability, relative magnetic permeability, where relative magnetic permeability mu r, which is equals to mu m by mu naught. So mu naught into mu r, which is equals to mu m. So B equals mu naught 1 plus chi times H, or magnetic intensity, where 1 plus chi will become mu r, relative permeability, and permeability of free space, and relative permeability will give us permeability of medium times magnetic intensity. So the final magnetic field, net magnetic field, when there is a soft iron core placed, is the permeability of that substance or that core times the magnetic intensity produced, where mu r, which is dimensionless quantity, which is called relative magnetic permeability of a substance. It is the analog of dielectric constant. It is similar to dielectric constants in electrostatics. The magnetic permeability of the substance is mu, and it has same dimensions as and units as mu naught. Mu, which is equals to mu naught times mu r, mu naught times 1 plus chi. The three quantities, chi, which is susceptibility, magnetic susceptibility, relative permeability, and permeability of medium, are integrated, and only one of them is independent. Given one, the other may easily determined. Okay, only one, if one of them we know, other two we can determine. With this, I will end today's video. I will continue from this example in the next video, hopefully. Then see you later. Good night.